Hello, everyone. Thank you for joining. This is our 8th talk for the year, and today we'll have Dr. Gray, and he will presenting a bit of on content on abstraction. So he studied at UCT and got all his degrees there, and then including his normal BSc degree, honors degree, and PhD, and then his interest of study now is in category theory, and to be more specific, he studies algebra via category theory. So thank you, Dr. Gray, for being here. We look forward to the talk. So you can start whenever you're ready.
Okay, thank you for the invitation to talk here. So yeah, I want to talk about abstraction and I mean, in mathematics, of course, not outside. So I said my title was an introduction to abstraction, and that's what I'm hoping to try and show you. Trying to give you an idea of maybe why we want to abstract as well as how to do it. So two things. So let's start with a question. What is a vector? Okay, so that's our question. So you probably, when you were at school, you probably heard things like, as an answer, something that has both length and direction, something like that, right? Am I right that this is something you probably heard before?
Yes.
Okay, so please do interact as much as possible. Makes it easier to know whether I'm saying something that makes sense or not to you. Is there no chat in this particular thing? I see. Okay, so that is the question that we might ask, and then so what I want to say is that in some sense maybe that's the wrong question. Is this the wrong question? Okay, so what could I possibly mean by that? Maybe what we should be asking is this question. What can you do with vectors? And if we change our question to that, we'll see that maybe it will open up the possibility of the things that we might think of as vectors. But they will have the same behavior as the things that we were trying to think about when we were first thinking about what is a vector. Okay, so let's try and think about what are the things we can do with vectors. Not worrying about what they are, they're kind of arrows, right? So let me draw in different colors some arrows. If I've got two vectors, let me use the ruler, why not? I can. So I have, say, this vector, let's give it an arrowhead. So I'm representing them, they have a direction, right? And they have a length. So there's one. Oops, that's not good. Here is another one. So what can I do with them? Well, one thing I can do with them is, I'm just going to keep this one over here and make a new one, is I can put them head to tail, so to speak, like this, and I call the thing that I get the sum of the two vectors. So if I draw in here, I can add vectors together, right? And this is what it looks like in terms of pictures. Adding vectors together is this operation in terms of pictures. So if I gave names to my vectors, maybe my first one was called U, and my second one was called V. I can add them together and I get a new vector which is called U plus V. Okay, great. That's something I can do with them. But so far, that's probably not enough. I'm not saying how. So now I could ask myself, well, how does this operation behave? And one of the things I could observe, which I wish I had copied my U first before I did this. Let me see if I can copy it now. No, let's see again. Maybe I can still copy it with, yeah, I can. Okay, I lost half the head, but that's okay. Is that I could try and add them in a different order and see, do I get something different? So if I start with V and then put U, I actually end up with the same result. So I've observed that these, whatever these vectors are, whatever they are, they have a certain property. What is that property? We've observed that we have this thing we can do with vectors, is which we can add them together. And we've observed that it has the property that whether you add them in this order or that, you get the same result. Okay, so that's one thing we can notice. Let's add in a third vector into the mix and see if we can see something else with it. Maybe I'll do a separate picture with it. Sorry. Let's draw 3 new vectors. I'll draw them separately and copy them so that I have them all. So here's my one. Here's another one. And my last one is like this. Let's draw all the heads. So here is my one vector. Here's my other one. And my last one is this one. Okay, so let's see what happens if we try and add up all 3 of these and we add them up in different orders. Let's see what happens. So let's take this first vector and let's add to it this vector. We get this as the result. We get a new vector, which maybe we'll draw with red, right? This is our new vector that we get out as an outcome. This is taking longer than I would like, this drawing of vectors, but never mind. So that's what we get when we add them that way. And then we could add further one last vector. So let's add the last vector in afterwards. So we take this vector and we add it in. And we end up with, let's draw in with this color, our result. Oh, I'm not on ruler. Our result is this vector. What color should we use? Oh, why did it change color? That wasn't good. We end up with this vector, right? When we add them all together. Right, so if I take the green one, then I add it to the blue one, then I get the red one. If I take the red one and add it to the pink one, then I get this light blue one, right? Okay, now I could do that in a different order. I could first take the blue one, and then I could add the pink one, and let's say I get the orange one from doing that. That would be this vector that I'm drawing in now into this picture on top here. And then I could add the green one to that. So the green one plus the result of adding the blue and the pink gives me the same thing as rather adding the green one, the green to the blue and getting the red and adding the pink afterwards. So if I write that down as an equation, I get another equation. I get that U plus V plus W, if I have 3 different vectors, then if I sum them up a different way, I get the same result, right? So I've got these two rules so far that I've discovered by thinking about how about our new question. What can you do with vectors? You can add them up, right? And they have certain properties. U plus V is the same as V plus U. U plus V plus W is the same as U plus V plus W. And there are other things I can observe. If I use a dot to represent the 0 vector, then I can observe that if you take U plus the 0 length vector, you end up getting back U. So that's something else I can observe. And then there's another vector that you can, for any vector I have. So if I take, let's look at this vector. So if I look at, I don't know why it's drawing lines here. Anyway, it seems to be. So if you look at this vector, there's another vector that when you add to it, makes it completely disappear. Which would that vector be? It would be a vector which is in the opposite direction, right? So if I have the same arrow but pointing in the opposite direction, if I add them together, I'll get just a dot. Do you see that? So if I took this vector and I take off its head and draw the head on the other end, then if I add these two together, I'll end up with just a dot. Do you see that? So this vector that I got from that one, I call minus my vector. And if I add them up, I'll end up going nowhere, right? If I was to put these together, I end up with going nowhere. So that's the 0 vector. So I have another vector, which is called minus my vector. And it has the property that when I add it together with my vector, I end up getting the 0 vector. Okay, so we've got these 4 properties of vectors. It turns out I can do other things to vectors, which you probably know about from physics, and that's called scaling them. So if I have a real number, I can scale my vector, I can stretch it by the real number to a new vector. And if I use, let's say, K and L to represent real numbers, then this new operation, so we have K times a vector, gives me a new vector, and it satisfies also certain conditions. One of them is this, that K plus L times by a vector U is the same as K times my vector U plus L times my vector U. So that's one of the properties that holds. There's another property that holds, which is that if you scale the sum of 2 vectors, that one we could illustrate, but I'm not going to because it would take a long time. If you scale the sum of 2 vectors, it's the same as scaling the one and then scaling the other. Okay. Then there is one more important thing that we can do with our vectors. What happens if we scale our vector by 1? If we take 1 times our vector, we get back our vector. Okay, so these properties hold for these things called vectors. Now, what is the idea of abstraction? So we have these things called vectors, and they have operations on them, and they have special vectors inside them, and they satisfy these conditions. Maybe there are other examples which satisfy these same conditions. So we had this idea of vectors, which gave rise to our list of properties, and maybe there are other examples. So are there other examples? Which have the same structure? Can I assume that everyone knows what a function from the real numbers to the real numbers are?
Yes, I think that should be fine.
Okay, so if we could take, instead of vectors, we could take functions. So f is a function from the real numbers to the real numbers. What does this to and from? In other words, if we're saying primitively, we plug in a real number and we get out a real number. Okay, so we're thinking of functions which have inputs real numbers and outputs real numbers, and we're thinking of those which have the property that every real number can be plugged in and we get an output. Okay, so if I have two functions, there's quite a natural way of adding them together. To describe a function is to tell you what it does to x. So this sum of f and g, I'll say, has the following property. So f plus g is f of x plus g of x. So I can add functions, right? Can I scale functions? So if k is a real number and I want to scale f by it, how should I do that? Well, I just take my f of x and scale it by k. An easy exercise shows you that all these rules hold for functions. I didn't tell you what minus f should be. What should minus f of x be? It is minus f of x. So plug in x into f and then minus that. And if you check, it won't be very difficult to check, all of these rules hold for the example where u and v are now replaced by functions. I didn't tell you what is 0. So what on earth is 0 here? What function has the property that if I add, so let's call it z. So we're looking for some function z that when I add to any function, I get back my function. So what should z be? Z of x should equal
0.
0, exactly. So we do have a function which behaves like this 0, and we have addition, and you can check all of these properties do hold for in the case of functions. So we went from asking the question of what are vectors to a different question, what can you do with vectors? And then we discovered, well, actually, if we think like that, then functions can be thought of as our new kind of vectors. So we've expanded the list of things that you can think about in this way. Someone's microphone is...
That's why.
Can I ask you to please turn off your microphone? Okay, thank you. Okay, so do you see what we've achieved so far is that by changing our question a little bit, we found a much larger collection of things which all exhibit the same properties. Okay, I've only shown you 2 examples. What would the other examples be? The usual vectors that you're used to from, so vectors in 2-dimensional space, vectors in 3-dimensional space, vectors in 100-dimensional space, they all will satisfy this. But so will functions from the real numbers to the real numbers. Okay, so, and there are many other examples. I don't want to spend time right now talking about them. I want to turn our attention to some other aspect of this. So far we've seen that if we change our perspective into, instead of thinking about worrying about what is a vector, we change it to what can you do with vectors, then we find conditions that we can do with vectors, and we find many other examples of them. Okay, so that's hopefully the perspective you got from what I've said so far. So now let's turn our attention to a different aspect. So now we forget about vectors and we're thinking about only things that satisfy these rules. So we say these are the rules. We have things, we have operations on those things, and they satisfy these rules. Is there any other rules that they satisfy automatically because of these rules? So let's see if we can prove some very simple things that follow from those rules. So one of those things that we might expect to happen is if you take 0, if you scale your vector by 0, what do you expect to get? If I make my vector 0 long, what do I expect to get? That special vector, the 0 vector, right? So now I'm not thinking of vectors though. These are arbitrary things which have the properties that I wrote down above. Maybe I'll copy them here so that we can refer to them, because we're going to try and prove now that what I just wrote down is in fact true, just following from these rules. Let's see if we manage. Would you like to try? Should we have a little break while you try and prove it? See if you can use only these rules that are in this box to prove that 0 times u bar must equal to u. I mean, must be equal to 0. I don't know whether you want to do this. If you don't want to do this, tell me, and I will not do that. I just thought it's interesting to see if you can. When I was in your position, I found it quite fun to try and do that for the first time. Maybe you've already done it before, though.
Hello, sir.
Yes.
Can we use the first condition?
You must use all of these conditions. Well, maybe you don't need every single one of them, but you can use any one of these you like to prove this. So, but we want to arrive to that this must equal that. So we don't know this. So we want to do some calculation. So we start with this, say, we do some steps, it equals that, which equals that, which equals that, which equals that, which equals naught. That's what we want to do. Right, so I can't just use this first one because it doesn't say anything about 0 times u. Right, it only says what happens when I add 0 to u. Let me do one now, and then maybe you can try another one. Should I do that instead? So let's try and prove this. In each step that I do, I should explain that I used only one of these rules. Okay, so let's start with 0 times u, right? And I'm going to try and arrive just using these rules to 0. Okay, so what I could do is say this is equal to this plus 0. I used the first rule, right? Everyone's happy with that? Okay. Didn't do much. Now I'll use, look, here I can write 0 as 0 is equal to u plus minus u. Right, that's one of my conditions. I know that 0 equals u plus minus u, so I get this. Okay. Then if I use, let's give names to these rules so that I can explain which rule I use. So let's say this one's called A, B, C, D, E, F, and G. So what did I do in this first step? I used rule A, right? This was rule A that got me here. And then in order to get here, I used rule D. And now I'm going to use rule C. So rule C says I can change the order of my brackets. Okay, so that was rule C that allowed me to do that. And then I will use rule G. So I get 0 times u plus. So if I use rule G, I can write this as 1 times u plus minus u. So that was using rule G. And then I will use, if I look at this, I want to try and take out these coefficients. Luckily, there is a rule that says that. That's rule E. So I can write this as 0 plus 1 times u, and then I add minus u. So that rule was rule E. Okay, and now those are real numbers. So I know that 0 plus 1 in the real numbers is 1, right? So I get 1 times u. That's just using properties of real numbers, which we will just assume. Okay, what is 1 times u bar? Well, according to our rule G, that's equal to u bar. So now I use G again. So, right, and then u plus minus u equals 0. So I've got what I wanted. So let me fill in the last steps. So this was using, I got to here using G. Then I used D again to arrive to 0. Does it make sense? So what have I proved? I've proved this rule up here, that if you have any situation whatsoever in the world, if it satisfies these conditions, then it also satisfies this condition.
Dr. Gray?
Yeah.
Is it, do you show, if you take only rule E and you make K and L equal to 1 and minus 1, because at the top you have 0.u, so 1 minus 1 is 0, and then you just use rule D afterwards, then it would also work. But is it skipping too much steps then?
No, let's see. It doesn't quite work. You prove you're using a rule that we haven't got. So let's see. That's very interesting. So let's try what you said. It's very interesting. So 1 minus u. Okay. If I use on the one hand, okay. So let's just write it like this, so it's easy to see. So 0 minus u is equal to. This is true. Everything you say is true here.
Yeah, okay.
Perfect. Then I use rule number E, yeah, to go, let's write it like this. So far I just use properties of real numbers, and now I'm using rule E. So I get 1 times u plus minus 1 times by u. Okay. So great. That was rule. Okay. Let's see what goes wrong here. It's not really wrong.
Oh, I see.
Yeah.
Is it because you? Oh, okay, Doctor, you know, go on.
So this will be u plus, and now I just can't do anything here. Oh dear. How do I simplify this? I wish this was equal to minus u.
Okay, I saw that now, but that didn't seem like a problem. But I see. Yeah.
So now you've opened up a new question. Right? Great. Now we've got a new question. Let's make it slightly more general than your question, but it's still the same sort of question. Is it true that minus? I left out one rule here, which we should add in. We need this rule as well, that KL times U. We will eventually need it if we want to do everything that you might imagine we might want to do with vectors. That should be called H. So, which you can also think about makes sense for vectors. But anyway, let's try now and show that K minus K times U equals minus K times U. That's something would be shockingly surprising if it wasn't true, right? which is why you assumed it was.
Yes.
So let's try and prove that. Would you like to try yourselves? I personally find it quite fun doing this myself, but maybe you don't. If you don't, let me know and we can move on. So let's correct my box while you're thinking about that. So we won't be able to prove this rule H. So we need to add it in. By the way, the thing you're doing in E can be used to help you with this, essentially. All right. Should I give you more time? Or you had enough? Should we do it? Should I leave it as an exercise?
I think Doctor can continue.
Should we go through it? Yes?
We can, yes. It depends on how much time Doctor has, like, or scheduled for it. But yes,
the main point is, well, I mean, I'm not going to try and make too big a point, but I'm just trying to show you that what happens when we abstract. Okay, so this is part of it. So why not proving this? So let's try and prove this. So how can I prove this? Well, let's do what we did before. Let's start on one side, and let's try and work our way to the other side. Okay, there are other ways that you can try and approach it. You could sort of think about what each of these identities gives you. So if I think about what property this has, I want this to have the same. So that's where I'm thinking along. So so this will be minus k times u plus 0. Okay, so I used only one property so far, right? Okay, this time let's write 0 as what? Well, this time let's use our u to be k times u. So we get k times u plus minus k times u. We need one more bracket there. So there I used, should I annotate with the rules? Is that helpful? Why not? So this is rule A, and this is rule D again. And then I can re-bracket. I'm sure you're starting to see where we're going now, probably. So what is that rule that allows me to re-bracket? That's what we call C. And then we need to use rule number E here. Well, I'm not sure I should call it number E. So that's rule E that allowed us to do that. What is minus k plus k if k is a real number? That's 0, right? So we get 0 times u plus minus k times u. So which rule? That's just a rule of real numbers, so I'm not going to write it. Okay, and then now we use our whole big proof that we wrote up here, right? We proved that 0 times u is 0, so now I can replace 0 times u with the 0 vector. and then I get this, and then if you add 0 to anything, you just get the anything. So we've proved our rule. So which rule did I use here? I actually used 2 rules. Let me be more careful. Oops. So technically, I suppose I should do this, right? So which rules did I use there? We eventually used rule B, which we hadn't used before. Rule B gives me to this point. And then rule A is it that gives me this point. Okay, so now these are tiny little theorems, right? They're tiny little things. They're not very deep results, but they are things that we know will hold no matter which example you take, right? If you take any example whatsoever which satisfies these rules, these will be consequences. So you don't need to check these rules anymore. These simple rules will automatically hold. Does that make sense? So it's a bit strange to say, but we proved that 0 times a function equals a 0 at the same time as we proved it for vectors. And minus k times a function is equal to minus k times the function at the same time as for vectors. And we know it for any example of anything which satisfies these rules. So what's the point of what I'm trying to tell you? So we said maybe this is the wrong question. Why? Because understanding the relationship between vectors leads to studying which properties they hold, which leads to finding a list of some of them. How do you find out which list? That's a more difficult question to answer, but let's say we found some list, then we can look at which other examples satisfy the same conditions. We found in our case the real numbers, and then whenever we prove any theorems that follow directly from the rules that we wrote down, we know that those theorems will hold for every single example that we have. Does it make sense? So this is kind of what abstraction does. You abstract away, you find more examples by doing so, because once you abstract, then other things can also have the same properties. And then anything you know follows from the rules that your abstraction satisfies will hold for your examples, all your examples. So you can find unexpected and interesting examples, and then you get unexpected and interesting results about them. We aren't in a position in this talk to have seen such an example, but I hope you get the essence. Okay, what about one last exercise for you to try maybe at home? So try and prove that the following holds, that k, it's not very difficult, times u equals 0 implies k equals 0, or u equals 0. Okay, I think I'm going to stop there.